Hello, everyone. Today I'll be talking about positivity bounds technique and how we can constrain EFT coefficients, effective field theory coefficients, from basic principles applied to both infrared and ultraviolet theory. So the framework is the following. We have some energy scale and usually all our theories work at low energies. So we have 0 energies, and here there is a cutoff scale lambda, maybe at least Planck mass or something lower, depends on the theory we consider. Here we can make a computation and our effective field theory description, which I was discussing yesterday, will be a good description. We can compute many things like scattering amplitudes, also maybe consider some dynamics on top of not very large backgrounds, which are within the effective field theory regime of validity. But at higher energies, we don't know with what kind of theory we can match it, but we can get some meaningful constraints if we assume that ultraviolet theory has several properties which are kind of look like very motivated. We want to be normal quantum field theory, or at least resembling the properties of normal quantum field theory. And here we want it to be unitary, so we require unitarity. We require Lorentz invariance to avoid theories breaking Lorentz invariance. Then the other requirement is causality. And all of these requirements, in principle, they are applied to all these settings. It should be there. And the last one, I would call it locality, and we'll formulate what I mean a bit later. So as we discussed, we can, working on top of flat space, we can compute S matrix, and we can concentrate on 2-to-2 scattering amplitude as the main object. Scattering amplitude in Lorentz invariance theory can be formalized as some function of two Mandelstam variables, as I've been discussing yesterday. On shell amplitudes, they are just functions of two scalar variables. Unitarity of amplitudes imply that at least imaginary part of this amplitude, when t goes to 0, is positive. But more precisely, you have partial wave expansion. I write it schematically. There was a precise expression. Or it depends on the type of the theory, but you always can expand it in partial waves, and partial wave amplitude should follow the properties required by full unitarity in principle. So its imaginary part of FL should be positive, and imaginary part of FL twice should be larger than modulus of FL of S multiplied by some factor. Let me just leave it like this. I discussed it yesterday. So we have some precise conditions for the scattering amplitudes to be unitary. In principle, we write it in terms of, we formalize it in simply mathematical statements. Causality can also be stated as the analyticity of function A of S and T in the whole complex plane. But along the real axis, we can have singularities like poles and branch cuts. This is allowed. Locality is a statement that corresponds, usually is thought to be the polynomial boundedness of the amplitude. That this function of two variables is bounded polynomially everywhere, including complex plane. Which is important, not only real axis. Yeah, but this is only for real S. Real and positive S. Locality is defined as polynomial boundedness of the amplitude in the whole complex plane. And this definition of locality for theories for scattering of massive particles for the theory with mass gap translates into Martin-Forsyth bound, which I derived yesterday, is that AFS and at fixed t should not grow faster than s log squared s. Okay, even though we don't know what is UV completion, we have this set of 4 properties translated into some mathematical properties of function of two variables, two complex variables, amplitude. And after that, we can use some, we can make use of analyticity property, which encodes actually causality of the theory to derive relations between infrared theory and ultraviolet theory. Yes?
Is there any theory in which the Froissart bound is saturated, but you get S log square S?
Actually, I don't know about that. Maybe some renormalizable theory should have such behavior. Yes.
So the claim is that you only accept effective field theory that satisfies these properties.
That have a completion satisfying these properties.
But you don't know about the completion.
Yes.
The statement is that if they had a completion, they would satisfy these properties.
Yes. That's a statement. So that's the formulation of the problem. Like find the bounds on low energy Ft such that UV has these properties. So the problem we are solving is to find which EFT can be completed. By the class of theories with described properties. So here, how can we solve this problem? The simplest thing which can be done is to take complex plane of S, set t equal to 0, and look at the forward limit bounds. Why we take t equal to 0 is that because here we know that imaginary part of the amplitude is positive, and it makes it convenient to find some bounds out of this. So if we scatter, we are dealing with a theory with mass gap. Here, assume it's scattering of massive particles, the analyticity structure will lead to two branch cuts and some place where there are no branch cuts. In principle, one can have poles here because there could be some exchanges by other massive states in the theory. Then, if we want to derive the bound on effective field theory or simply relate infrared and ultraviolet theory, analyticity would be very helpful because in principle we can compute something which we know how to compute. We can compute integral over this contour. Let's call it gamma. This is some computation which can be done fully within the effective field theory. And yes, here effective field theory breaks down. So we don't need any knowledge about UV if we just set a question that let's compute small contour integral along all the poles which are there. So we can define a quantity. I label it IR, sigma IR. It would be with factor 2 pi I integral over contour gamma of amplitude of mu0 over mu minus mu0 cube. And I pick my mu0 point here. It doesn't matter where precisely I take it, but it should be between 0 and 4m squared. And also lying on the real axis. Then I have two ways to compute this quantity. One way is to express it as a sum of residues and assume that there are no poles except for artificially introduced mu0 point. Then it will be simply 1/2 of second derivative of the amplitude to the point mu going to mu0. Okay. So this quantity is again something related to only infrared theory. So I'm assuming here no extra poles. Then what do we obtain? Imagine we are dealing with some scalar amplitude, as I was writing yesterday. One of the example would be like squared plus t squared plus u squared plus bstu and other terms. What can we constrain this way? This way we basically can constrain this quantity will be just equal to a coefficient in front of s squared. Because I take a derivative, I get factor 2 and I have 1/2. So in this way I can extract coefficient a in my amplitude and then let me find another way to compute sigma IR. Another way is related to the use of analyticity and translating it to some properties of ultraviolet theory. I can deform this contour and make it going along both branch cuts. So it will go here. Then I have to close it. It goes here, it goes here, and goes here. And I close it fully to this large circle. Okay. Since we are sure that an amplitude is analytic, I can do this deformation and I can compute it like, let's put gamma tilde. So it will be the same 1 over 2 pi I integral over gamma tilde now of the same amplitude. Then I can split it to two separate integrals. First of all, integral over infinite circle will be 0 because we have Martin-Froissart bound, and it will have just the form that I'll take a of mu exponent of I theta d. So literally, to estimate infinite circle, I need to compute this one. And since my amplitude behaves as S multiplied by log of R exponent of 2I theta log squared. So my contour integral over infinite contour of the whole amplitude will be bounded from Martin-Froissart bound. It's R log squared R, some angular variable where theta is going from, basically it will be integral from 0 to 2 pi. Sorry, but d theta. So I'm integrating with respect to the angle and R going to infinity. Of course, it will be just 0 because I'm getting here I'm getting R squared over R cubed. So it should be pretty clear that under if Martin-Froissart bound is valid, the integral will be 0. Moreover, even weaker condition like amplitude is less than S squared will also be like maybe 2 minus alpha will also lead to vanishing of infinite circle because the integral will simply go to 0 in the limit R going to infinity. Okay. For this reason, I can simply write my integral here as two integrals, one from 4m squared to infinity. And it will be an integral of a of mu 0 over mu minus mu 0 cube. A of mu plus I epsilon minus a of mu minus I epsilon d mu. So I have to take discontinuity of this amplitude because since it has a branch cut here, it behaves differently here and here. They are not the same. So I need to take the quantity which is equal to a of mu plus I epsilon minus a of mu minus I epsilon. And I need to sum it with the integral from minus infinity to 0 of the same quantity, basically. Then it will sum up to it will sum to the integral, one integral in principle, from 4m squared to infinity of a of mu plus I epsilon minus a of mu minus I epsilon. And in addition, I will have 1 over mu minus mu 0 cube plus 1 over 4m squared minus mu plus mu 0 cube. Because I can shift the variable mu here, so mu goes to mu 4m squared minus mu. And if I keep all the signs correctly, I will get back to the expression where mu where we have mu 0 with plus, and here we have also plus sign. And the amplitude of minus s here can be translated to the amplitude, physical amplitude, which is in basically U channel amplitude. So we know that its value has the same properties in the U channel. We have also unitarity there, and discontinuity has the same value there, 1 over 2 pi I, and also this discontinuity is nothing else but imaginary part of the amplitude. So A of mu plus I epsilon minus A of mu minus I epsilon is equal to 1 over I, imaginary part of A. Because we have a property that the complex conjugation of the amplitude will be the equivalent to complex conjugation of the argument. This is dictated by analyticity properties of the amplitude away from real axis. So if the function is analytic, it will have this property. Power 3 is to take the first constraint, which where I can neglect the infinite circle. It is following from Martin-Froissart bound. I can also take mu like power 5, power 6, and so on. No, in scalar amplitudes, I cannot take power 4 because I will get 0. Because if I have even power here, these two things will be canceling each other. So I just get 0. But it can be still a non-trivial bound if you are working with non-crossing symmetric amplitudes, like amplitudes for spinning particles. So, but in the simplest case, we can find a bound for even powers or for odd powers of mu here and even powers of s in the amplitude here. So this quantity should probably not one, not it will be equal to I, imaginary part of A, right? Then here I have instead 1 over 2 pi integral of imaginary part of A taken at t equal to 0 over 4m squared to infinity over okay, it gets multiplied by the same factor from same combination of these functions. Then I can conclude that this integral is strictly positive. Why? Because this function is strictly positive by unitarity, and this particular function is also positive when mu is between 0 and 4m squared. So if mu is less than 4m squared, this is a positive quantity, and this one is positive too. So this way I derived that basically from this amplitude, or more general, like second derivative of the amplitude, taken at t equal to 0 will be always positive. In the theory consistent with UV completion having listed properties. And it applies that A is a positive number. So why can we expect that this bound is interesting for some applications of this series? First of all, it was historically the first positivity bound derived in this way, also as an implication of causality. It was derived in a paper by Sergei Dubovsky, Arkani Hamed, Ricardo Ratazzi, and I don't remember other names of the authors of this work. Basically, they were interested in theory with Galilean symmetry, which would be the theory having the form of phi squared plus, and then they introduced the term which yesterday I've shown that it's redundant in the sense that it can be brought to higher order terms. But this particular theory, in principle, we can not do this field redefinition and just consider this theory. It has a non-trivial amplitude, the same as would be given from theory which after field redefinition. But why it is interesting? Because it has an additional symmetry. We can, in addition to shift symmetry, it has a symmetry of when the field phi is going to field phi plus some space-dependent factor, a rho x rho, where x is space-time coordinate. So this Lagrangian has these properties, and it's easy to show because if we act twice, like two derivatives by acting by box, of course, this box phi is invariant. But d mu phi squared will be transformed to d mu phi plus a rho plus a mu plus constant, and d mu phi squared is transformed to d mu phi squared plus 2a mu d mu phi plus a mu squared. For the kinetic term, it is invariant because we are getting these additional terms, which this one is total derivative and this one is just constant, which can be added to Lagrangian. Of course, we consider no gravity at this moment, just field theory. And when it is multiplied by, if we multiply it by box phi, which is not transformed, then we can notice that a mu d mu phi box phi is a total derivative because and box phi here is simply the total derivative. A mu d mu phi box phi, here you can You can write it as a mu phi box so it can be also brought to the form of the total derivative. So it will be equal to minus a mu phi box d mu phi, which is basically we got simply the same expression as it was before. So yeah, we can bring this expression to the same form as it would be done before. So we just put box over this field, and it will be minus a mu. Since we are emitting total derivative twice, we don't change the sign. So box is acting on phi. It's a mu box phi d mu phi. So we got that a mu d mu phi box phi is equivalent to minus itself, and it means that it's just 0. Sorry, I forgot a bit how it was derived precisely. But apparently, we can get that there is an additional symmetry, which was in addition proven to be consistent with quantization, so it should be non-anomalous symmetry. For this reason, people were really surprised to get that this symmetry cannot be consistent with UV completion with good properties, because this bound basically, this Galilean theory starts, the amplitude expansion starts from beta STU. There is no a squared term, but we just derived that there must be some a squared term, which means that I must add the d mu phi to 4 term to guarantee the good UV completion for the theory, but apparently d mu phi to 4 term is already non-Galilean symmetric. It violates the Galilean symmetry. So apparently positivity bounds can be in contradiction with some nice symmetry, and this is quite interesting. Also, the application of positivity, even the simplest positivity bounds, to theories with massive gravity brought results which are also very constraining for the theories. And the reason is that usually scalar degree of freedom appearing in all massive gravity proposals resembles this Galilean. It needs, for consistency, it needs to have kind of Galilean symmetry in the low energy regime, which is not compatible with good enough UV completions. So for this, we need to add mass to this term and softly break this symmetry. But this again leads to problems and the additional constraints, making phenomenological applications of massive gravity having lots of troubles. So this technique was kind of a key, almost a killer of massive gravity. But apparently, it can be developed much more. We can go far beyond this simplest linear bound. Yes.
Massive gravity is not consistent.
To be precise, massive gravity needed for some phenomenological purposes is in tension with the positivity technique.
Even these assumptions.
Yes, of course.
So does it mean that logically you need the massive graviton to be very, very light?
Yes.
If you take this A, then that corresponds to a large mass.
Yes, like this. So it's hard to have it light indeed, and that's a problem. It's like a requirement that cutoff scale must be very low. If you have light massive graviton, then cutoff scale is very, very low for order of the mass, and this is a bit in tension. Like
maybe some of the full principle will not apply to some UV completion of massive gravity.
Yeah, that's also the case.
The Galilean is the coupling. You can see the Galilean as appearing the coupling leading of massive gravity, right? And there is some work, I think, by Tolle, where he says that maybe a UV completion of the Galileo has to be non-local,
Yeah.
for the reasons. And that could be a reason why maybe for massive gravity you cannot just maybe have some local UV completion. Because anyway, some decoupling limit people claim that.
Yeah, well, the conclusion is just a tension with all these principles applied to UV completion. In principle, you can say that I don't care and proceed to.
You don't really care, let's say, about the phenomenological application. The theory is still good, right? From a purely theoretical perspective.
Which kind of theory? I think there still some range, should be still some ranges where it is working. But as I understand, the bound is like telling you that you must have cutoff scale of order of mass of this field. Whether you can say, in general, it's not very good, but it looks like you have some state with which is very close to cutoff, and then applications are a bit tough. Okay, so this is just very simple bound which was derived a long time ago, but let me extend this technique and show that apparently bounds can be much stronger. Of course, you can write a lot different things, and the technique which we found working like the easiest and the best for deriving bounds. I'll tell this because maybe some people want to apply it to different theoretical to different theoretical proposals like asymptotic safety and so on, and it could be useful to understand how more bounds can be derived, more strict bounds. And we found it useful to take not exactly t equal to 0, but take small t, like approximately t equal to 0, but then we have the picture like this. Also, here I switch to extend to consideration of probably massless theories. For massless theories, I can have a branch cut going here. And then directly, I cannot directly use the described technique for massless series, but what I'll describe now will be also applied to gapless series without any problem. So imagine I take integrals over, I'll use a bit modified contours, compute arc integrals. This will be my complex plane mu, or complex plane S. I can also close these contours. Here is my cutoff scale, and here is epsilon squared, lambda squared, some point which is maybe a bit close to cutoff, but I have a parameter epsilon to regulate how far from the cutoff scale I go. So so the idea is to compute integral over this kind of arcs instead of computing integral over small point. But this is still, these arc integrals are still computable within effective field theory. And I'm computing integral over arc of the same amplitude A of mu t over mu minus s for example, cube. I can take 1 over 2 pi I to get it real, and then I can transform it to integral over branch cut here and branch cut here. Even though it lies in the range where like we don't know what is the theory, we know that imaginary parts will be positive. So I can rewrite this integral as integral from epsilon squared lambda squared to infinity d mu over pi. Here I write discontinuity of A as discontinuity of A over mu minus s cube plus integral. Strictly speaking, it has since I'm shifting from I'm doing the shift of the second integral at t which is not precisely equal to 0. I have like t dependent lower bound of the integral, which may be sometimes relevant, but usually not. And here I have a discontinuity of the amplitude in the U channel. Mu minus U cube. So I can write it in terms of that. And both discontinuities, like discontinuity of S, A, and discontinuity of U, A are positive. Yes.
Like with the internal circle.
With this,
yeah, this one.
The reason is that I want to derive some bounds which are stable with respect to loop corrections. I will also comment a bit about this. So this choice allows me to kind of more freedom to select the radius of this arc. In the previous approach, I had to take it at the point 0, basically. Take a limit mu 0 is going to 0 or being very small. This is an extension of the framework for massless theories, where we, instead of Martin first start, we assume additionally that amplitude is not growing faster than a squared, so we can avoid infinite circle. And we also want to understand how to deal with branch cut, which goes along all the way around. So this is, yeah. So instead of, I could introduce Paulet as equal to 0, but it's not that convenient, I would say. Then, yeah, for me, it's more convenient to set s equal to 0 at the end of the computation. But in this way, I can derive this quantity first. What's new is happening because here it's minus u, which means mu plus s plus t cube.
Lambda is still ultraviolet cutoff.
Yes. Lambda is ultraviolet cutoff. And then I can take derivatives of this expression and obtain bounds also on the terms which, for example, if I want to bound the term beta stu, I need somehow to extend my technique to t derivatives. Otherwise, I will never see it in the forward limit. For this reason, I want to write it like this, small t. And apparently, I need to let me make a couple of general definitions. I will call C and M quantities which correspond to 1/2 n factorial over 2 pi I arc integral of t derivative of m times of amplitude of mu and t over pi mu to the power n plus 1. And all of this taken at t equal to 0. Or maybe limit taken at t equal to 0. This will also be, in theory, which doesn't have any additional poles, it will correspond to, so I mean, if we have only branch cut here and the analyticity here, it will correspond to 1/2 of derivative with respect to t taken m times and derivative with respect to s taken n times. A of s and t. So once I define I define that, I can relate and also I will define integrals s and or u. They are defined as integral from epsilon squared lambda squared to infinity d mu over pi dtm of discontinuity of s discontinuity or of amplitude parts s or u parts. They in fully crossing symmetric theory, as and au are the same, but in principle it can be extended to theories with different which don't have SU cross full STU crossing symmetry. It will be taken at t equal to 0. So the difference here is that we tend to take this external parameter s to be going to 0 too. But first we take derivatives. So in this case, the problem I need to solve is to bound C and M coefficients, which are directly related to amplitude expansion. I need to express C of NM is some combination of I of NM. Regarding I of NM, they are positive. So this is a bit non-trivial statement why we are getting them positive. Because we know that imaginary part is positive, it's fine, but y derivatives has to be positive and the limit equal to 0. This follows from partial wave expansion and from properties of Legendre polynomials. Basically, imaginary part of mu and t differentiate like d over dt will be d over dt of sum of partial waves. So it will be 2L plus 1 Legendre polynomial L of 1 plus t over 2s. I consider massless case here for simplicity, and there will be imaginary part of FL of s. Imaginary parts are positive, that's fine. When I differentiate it, I differentiate Legendre polynomials, so everything depends on the values of Legendre polynomials at 1. T derivative of Legendre polynomial at 1. So it will be 1/2 basically, 1 over 2s additionally, PL prime of 1, imaginary part of L of s, and this will be positive. So you can simply compute what is it. PL prime of 1, if I remember correctly, will be L L plus 1 over 2. So that's some quantity which is always positive. It might this statement actually also holds for theories defined in more space-time dimensions, because instead of Legendre polynomials, there will be corresponding Eigenvalue polynomials. By some coincidence, they also have such a nice property that you can differentiate them with respect to t and also get positive quantities. And also same happens for spinning particles. You have another polynomials which are called Wigner D matrices, but again, they have the same property. They can be expressed through normal Legendre polynomials with positive only coefficients. And given that, and given the property of Legendre polynomials, some funny mathematical coincidence, we are getting that all discontinuities and their t derivatives, which is more important, they has to be positive. But let me also mention that if we are taking physical t, which is negative, then this continuity taken at finite, negative t, can be negative. It holds only in the limit t going to 0. So technically, all these relations and bounds can be obtained from taking representation of the amplitude. S squared integral epsilon squared lambda squared to infinity. Is continuity of S A over mu squared mu minus S plus S plus T squared integral to infinity epsilon squared lambda squared discontinuity U of A over mu squared mu plus S plus T. Then it can be done like, to avoid mistakes, one can do it on Mathematica. Simply take this amplitude described in this way and take derivatives with respect to S and with respect to T. And from that, one can derive easily. Of course, we already have different way of derivation, that C to 0 will be IS to 0 plus IU to 0. We already had this derivation. It's almost obvious. Then if we want to imagine we want to consider theory without crossing symmetry, then we can define C30, so it will be S cubed term, which will be non-vanishing. But we took some amplitude, which is, say, one of the amplitudes of graviton scattering. This will be 3IS of 30 minus 3IU of 30. And we cannot conclude that this S cubed coefficient is positive, but we can still do something with that. And the trick is that apparently we have a nice inequality, which is almost trivial, but very useful. Integral of n plus 1 m is less than 1 over epsilon squared lambda squared. Integral of S or U, doesn't matter, of n m. How can we see it? We need just to write the definition, basically. It's like it will be integral of discontinuity of A over mu to power n plus 2 d mu And since it's an integral starting from epsilon squared lambda squared to infinity, so it will be mu n plus 1 mu. And this function is always 1 over mu is always less than 1 over epsilon squared lambda squared, because mu is growing and this is becoming less and less. So it's always less than this value on the value taken on the boundary. And from this trivial statement, I'm getting epsilon squared lambda squared integral dA over mu to power n plus 1, which is like I'm just have this inequality. This is very useful because apparently I can derive the bound for S cube term, would I have it in the theory. And I can simply write that the combination of C30 plus 1 over epsilon squared lambda squared of C20 should be with coefficient 3 because of here will be positive. Because I simply can add to the right to the left hand side, I simply can add this C to 0 and compensate this negativity by having this extra additional positive term. And still I'm getting some non-trivial statement about the relation between C30 and C20. S cube term, and it corresponds to S cube term, and this corresponds to S squared term. So in a bit more complicated way, we can also derive that C21 plus 3/2 C20 minus 1/2 C30 should be positive. This is the best we can get. So again, playing with the relation between the C21 and integrals. When I'm trying, if I compute C21, I need to, why I'm getting negative contributions. Imagine I take 2 derivatives of S and 1 derivative in T. When I differentiate in T, when I differentiate with respect to T, I'm getting negative parts from here, because I have 1 over T here, and it becomes, it brings me some negative contributions, which I need to compensate with the use of some, oh, here I forgot to write it. So we can get this kind of bound. And of course, epsilon is in our hands, and the best bound is usually taken if epsilon is going close to 1, because that's why we want to make this contour as large as possible, as long as we can trust effective field theory. So another important bound is basically the bound for on S242. C40, of course, it's positive. I mean, in principle, even in the previous technique, we can use mu to 5 instead of mu to 3, and get the bound on fourth derivative instead of second derivative. It is very straightforward to do it. Now I can derive another bound, which is important because it makes like it's first evidence that compact that the parameter space of EFTs is a compact. So apparently one can obtain this bound, simply taking C to 0 and noticing that in principle I can do minus 1/12 of C for 0 and get still something positive. So this bound is quite important because I'm getting that S24 term, the coefficient in front of S24 term has to be bounded between 0 and the coefficient in front of second derivative with respect to S. In principle, all you can write many things, many linear bounds, what is called linear bounds. But the main observation is that we will be always getting compact bounds after fixing one of the terms. So the main observation is that if we fix C to 0 to be some constant or define cutoff scale, in principle, one can set it to be 1 because then it's a definition of cutoff scale. After that, we'll get some compact parameter space values, like all C, I don't know, we have some multi-dimensional space. After fixing that, we are getting immediately that all good enough theories live inside some compact range. Let me also stress that this is a three-level statement that we are considering like three-level EFT amplitudes. This is solid statement if we are dealing with only three-level amplitudes or loop amplitudes, but in massive series, in gapped series where we have some range where amplitude is can be expanded in series, can admit some series expansion. So the statement is that after fixing one of the Wilson coefficients, we have compact range where all the rest is living. And this is some compact multidimensional space of parameters, which usually it's sometimes it's much easier to write set of inequalities, but then it's a big problem to interpret them and understand because we have to plot to visualize the bounds. We need to plot a set of inequalities over infinite. Well, literally it should be infinite parameter space, but even if we have some like 5 parameters, we are already in trouble because we cannot plot 5-dimensional space. We need to do some projections or take slices of this strange figure, and sometimes we can obtain very strange figures. And apparently, so far it was observed that all theories with known UV completions, like expansions of EFT expansions corresponding to integrating out of some heavy particle, all of them are lying within the range defined by positivity bounds. So that's one of the ways how we can derive many nonlinear bounds. In principle, it was claimed in the literature that these bounds can be improved if one combines these inequalities with arbitrary coefficients and does some numerical procedures of optimizing this system. So this leads to big improvement in squeezing the allowed parameter space. That's one way. And in addition, we also can have a technique allowing to get bounds, get nonlinear bounds, in fact. In addition to this, we can make use of several integral inequalities. And one of these very useful integral inequality is so-called Cauchy-Schwarz-Bunyakovsky inequality. It is known as an inequality for integral of two functions. That integral of the product of two functions is less than product of integrals. I'm now mentioning this way of deriving inequalities because it was shown to be more constraining than the use of just linear inequalities. So, and another feature is that one can write some inequalities which don't contain explicitly the epsilon parameter and the cutoff scale. So they are kind of, there is no cutoff scale entering explicitly into this. And if it is applied to, for example, an implication of this inequality would be that integrals corresponding to 3,0 squared is less than integral corresponding to 2,0 and integral corresponding to 4,0. And just relating integral parts defined here, like integrals of discontinuities to basically Wilson coefficients, which are C and M. If they are defined like this, then we get for third C30 squared is less than C20 C40. So we can see that again, it's an evidence that Wilson coefficients are squeezed between some compact parameter space. Recall that we derived that C40 is less than C20. So C30 will be also squeezed in a compact range, compact allowed range for this. And this bound is important if theory is non-crossing symmetric, but one can also derive the bound on C21 in a similar way, and it is based on the fact that integral of discontinuity of S over mu to 4, which will appear when you differentiate with respect to t, d mu squared is less than integral ds d mu over mu cube multiplied by integral ds d mu over mu to power 5. This is an implication of Cauchy-Schwarz-Bunyakovsky inequality. We need just to identify that f squared is ds over mu cube and g squared is ds over mu to 5. And then simply applying this Cauchy-Schwarz-Bunyakovsky inequality, we can get directly this one. And for C21, for the combination C21 minus 1/2 C30, we get an expression through integrals as IS of 2,1 plus IU of 2,1 minus 3/2 of IS plus 3,0 plus IU of 3,0. And after that, I have a negative part, which I know that is less than IS20, IS40, and that's why I can eventually come to the nonlinear inequality, collecting all numbers, we get S21 minus 1/2 S30 plus root 3 over 4 root C20 C40 should be larger than 0. And apparently, these two inequalities cover the set of linear inequalities parameter space, as we noticed in when doing our work on bounding photon AFTs. Up to my computational experience, it happens that all set of linear bounds is simply encoded in these two nonlinear inequalities, and they're all enough to get bounded parameter space in EFT of photons. And another observation is that in principle, for t equal to 0 bounds, we must have the bounds of the form in general C2n 0 squared less than some n-dependent coefficient C2n plus 2 C2n minus 2. This is also important to mention because the structure of AFT, the structure of good enough AFT must be such that it doesn't allow to have a hierarchy between Wilson coefficients. So we cannot have Wilson coefficients to be very different, because we need the upper Wilson coefficient. So the Wilson coefficient in the middle must be squeezed between upper one and the lower one. It means that we don't have much freedom in selecting coefficients in front of s to power 2n coefficients in the amplitude. This is a bit more tricky if you have t-dependent part of the amplitude, but if it touches only s to 2n, we have a very strict rule that we should not have any large hierarchy. Positivity bounds do not admit hierarchy between these particular coefficients. So they should be kind of the same order of magnitude. So seems I have 10 minutes, and let me now comment what happens if we consider loop corrections to all of this technique. There are some things which, some new things which appear if we go to loops. And let me schematically comment on what becomes more complicated, and basically why at all we are using this kind of arc contour after thinking what is the best to do and how to justify the bounds if we consider there are loop corrections. So in the shift symmetric scalar, the amplitude was let's take first t going to 0, like t to 0 bounds, and the first loop correction will be, so we have normal s to 4 term, and also we have the one corresponding to beta function, as we noticed. It will be some coefficient b, which depends on, which is proportional to square of coefficient in front of s squared, like a2. And we have a combination log s plus log minus s. This combination, then if I compute arc integral out of this function, of course, if I compute integral for s to 4, it will pick for me just derivative, just coefficient a. But if I compute the arc integral amplitude over mu to 5. So I want to pick force, like I want to check whether the loop correction will affect my bound on the coefficient A. For this reason, I take power 5 here to get force derivative, and this integral will give me A plus 2B log S. To be log epsilon squared lambda squared. Because I have to substitute the radius of the arc. And here I might have some renormalization scale, mu squared. And apparently, I can still get my Wilson coefficient, but I know here that if I take an arc of epsilon squared lambda squared, the scale at which I can bound my Wilson coefficient would be actually the scale epsilon squared lambda squared. So I can my bound, since these Wilson coefficients are running with loops, my bound just says that the coefficient, I have to pick the coefficient and the scale epsilon squared lambda squared. Why it is bad to take just one point equal to 0? Because if I take, imagine I take epsilon equal to 0, I get some divergent thing, which I cannot bound my constant coefficient out of this. For this reason, it's much more convenient to use the arc integral of the radius, which you can vary, and the rule tells that it's better to have it as close to cutoff scale as possible, because this will also suppress loops. That's one issue appearing with loops. So in fact, we can bound the Wilson coefficients near cutoff, their values near the cutoff scale. But there is another nice feature which tells us, okay, let me extend it to S to 6 to show this feature and take arc corresponding to 6 derivative of this over mu to 7. And if you do this computation, this arc will give you C minus B over S squared, B over epsilon squared lambda squared. That's a result of computation of arc integral precisely. So in principle, I wanted to bound my coefficient C, at least to say that C is larger than 0. But I picked somehow the loop correction. It's not negligible here. The reason is that if I differentiate 6 times S to 4 log S, of course I get 1 over S squared at the end. That's why taking S to 0 is very bad here, because the loop correction will dominate in the quantity I'm trying to bound. So I will not be able to bound 3-level coefficients. I will be bounding at best beta functions. In principle, this technique in the limit epsilon to 0 can very nicely bound beta functions. And obviously, I get that my B coefficient must be positive, which actually corresponds to my result of the loop computation. There is no problem. But it is not that useful as using all this technique for bounding 3-level coefficients. So in order to justify 3-level positivity bounds, one has to take all these Wilson coefficients near cutoff scale with this epsilon and compute arcs instead of simply derivatives or small contours around 0. So that's kind of our observation how to admit loops here, but sometimes there are still even more issues. If we are coming to different T derivatives, then let me remind, yesterday I obtained a loop correction in a shift symmetric scalar, and it has also, in particular, it has a term t squared plus 1 over 21 s plus t log t. So why this term is not so good? This term is not so good for computing C22 because it corresponds to differentiating twice in T and twice in S. The problem appears because I have a term which is behaving as a square T squared log T. If I differentiate it twice with respect to T, I get basically log T. And then if I want to take T going to 0, I'm in the trouble. It diverges and I cannot use the dispersion relation in this case. So it means that taking too many T derivatives is also dangerous for bounding Wilson coefficients with the described technique, and we need to. This problem is even more serious than the one with log of S, because log of S can be killed by taking large enough arc, but this one is just infrared singularity, which doesn't lead to good possibility to like spoils all this technique for bounding many T derivatives. But still, what is very much possible is to bound beta functions, and in principle, all Wilson coefficients at tree level can be bounded, again bounded in compact ranges through their contribution to beta functions, because beta functions are like of higher order terms will be combinations of powers of tree-level Wilson coefficients, which are not very much affected by loops. So again, it seems like it's just not a very successful technique for bounding massless series with massless states. But in general, the conclusion that Wilson coefficients should live in compact ranges should be still valid for all of them. But I will comment a bit on what is special about gravity in the next lecture. That with gravity it's a bit more problematic than in the theories without gravity. And now I think I'm almost at the end of the lecture, and if there are questions, we can discuss.
If I understand correctly, you get the form of the loop and you want to just bound the coefficient. You cannot predict the form of the loop.
Well, I can predict it from unitarity if I have a theory.
As an input, amplitude at one.
Yes.
You want to have a bound for the coefficient.
Yes. Yes, I want to have a bound to the coefficient.
Question is, can you predict the form of the loop, not only the coefficient?
You mean the structure, like S squared T? For lower order coefficients where I can use elastic unitarity, where I don't have much many particle processes, I can compute it easily. But in more complicated theories, I need either the Lagrangian and compute all loops, because including all vertices, like 5 to 6 vertex, for example. It will contribute too, but it's not seen in the tree-level amplitude. So I need to have the full, at least the full Lagrangian.
Can you compare the result with some known theory?
A result of what? Of this one, which is
bound with the region. You must have some theory.
Yeah.
It's a theory.
Yes, the regions. Well, yes. This was done for different theories, like scalars. Also for gravity, people used like compared positivity bounds with predictions of certain string theories. In addition, in my work, we also have done some comparison with known partial UV completions, like we were dealing with photon AFT after integrating out of all fields. And if you integrate out of, say, fermion, then since it was a UV complete theory, you can predict the values of Wilson coefficients. And for all normal UV completions, we get them inside of the allowed regions. Basically, we got them outside of the allowed region for the case when it was spin 2 UV completion, if it's interesting for someone. For all renormalizable UV completions, it was always inside. But spin 2 sometimes doesn't work with positivity. There are some kind of partial, of course, not full UV completion, but partial UV completions when there is a spin 2 particle in it's appearing at some scale in QED, and then you integrate it out and get some chain of Wilson coefficients. So we simply made a comparison and noticed that spin 2, some of the series of spin 2, they have not predictions which are outside the region. No, interacting out massive spin 2 particles. Yes. Yeah. I think not charged, but some other interaction which can be written, like spin 2 field interacting with photon. Then you integrate it out, assuming it's heavy, and see what you get in Wilson coefficients. Gravity, yeah, we consider it gravity is one of the cases, and there are some other cases. So I don't remember the details. It's like it's in the paper. Our work was my work with Claudia Duram and some other people from Imperial College. We have done it we studied photon EFT. But the results about partial UV completions we just borrowed from the relevant papers. It's not our computation.
All this is try to get enough bound to get few solutions. Is that the idea?
Yes, in principle. Well, we are just checking what are the constraints on low energy series. And surprisingly, it was found that we need compact islands of parameters in the parameter space. Yeah, by the way, string theories fit there. They are living inside.
In the back of your mind, there is an idea that eventually the only solution is string kind of string theory.
Not obligatory, depends, because in principle, from all of this technique, we are obtaining some compact ranges where series can still live. Whether the amplitude is unique, I don't think that it's unique, because there could be different particle content and it can be different in this case. I don't think that it's unique. It should be some range anyway. Moreover, I don't know if there is any mathematically reliable proof that the bounds, the inequalities which we are writing, and not these inequalities, but even more some rules presented in the papers. I don't know if there is any proof or understanding how to get to build the procedure which will get the smallest parameter space left after applying all of them. It's not because this is like conservative. Of course, if we have that, if we have these assumptions, we know that these inequalities must be satisfied, but it's not a proof that they are the best, the most optimal. So the proof should be like a maybe bootstrap technique and reconstruction of the amplitude, but this is much more complicated, and I don't know if it's fully. It can be easily after that you can easily implement it and comparing with phenomenological theories. At least as far as I read the relevant papers where people tried to do bootstrap technique and bound same photon EFT, for example. I noticed that these bounds are apparently stronger than those they obtain, but they also claim some numerical problems that the methods don't converge well. So it looks like, I don't know, maybe for now they know better what's going on, but it seems like it's an open field of study.